So now we're going to be looking at work and energy problems. So here we're going to start using and these problems we're going to be using the definition of work, which is work is equal to force times distance. So how much work does a supermarket checkout attendant do on a can of soup? He pushes 0.6 meters horizontally with a force of 5 newtons. Express your answer in joules. Let's not do unit conversion stuff. It's not that important for the AP Physics exam. So in this case, a work would be force times the distance that they applied the force. So applied 5 newtons of force times 0.6 meters, and that would be 3 Newton meters, or joules is the units we use for work. Okay. Calculate the work done on a 1,500 kilogram elevator car by its cable to lift it 40 meters. So it goes up a distance of 40 meters at constant speed, assuming friction averages to 100 newtons. Okay, so we got to do a free body diagram. We have to say, what are the forces acting on this thing? Well, we have the tension from the cable moving up, and we have force of gravity pulling down. We also have some friction pulling down. Okay, now the reason we have to do this free body diagram, wasn't clear, is the work done by the lift force, but the tension, or you could call this a lift force. The tension is the lift force. The work done by the lift force is going to be the tension times the distances traveled. So I need to know what the tension is in order, or the lift force is, in order to calculate the work done by it. And so that's why I have to do a free body diagram. Now the net force in this case is T minus the force of friction minus the force of gravity. And this has to equal mass times acceleration. But because it's moving at constant speed, the acceleration is 0. So the net force is actually equal to 0 because the acceleration is 0. That means the tension has to equal the force of friction plus the force of gravity. The force of friction we knew is 100 newtons, and the force of gravity is just mass times 1,500 kilograms, mass times 9.8 meters per second squared, mg. So the tension we find is 100 plus 1,500 times 9.8, 14,800 newtons. So then the work done by this tension, or this lift force, is 14,800 newtons times the distance that it did that work for, 40 meters. And that's 592,000 joules. So that's the work done. What is the work done on the lift by the gravitational force in this process? So work done by gravity is also the force of gravity times the distance. Now the force of gravity is mg. But one thing to note is that the force of gravity is opposite to the displacement. Like if we're gonna we have to keep in track our signs. We're gonna say up is positive. That means the displacement, the distance that we travel here, d, is positive 40 because we go up 40, and we're saying up is positive. That means the force of gravity is actually negative because gravity is going down. So negative mg times d. So this is negative 1,500 times 9.8 times 40. And that's negative 588,000 joules. I don't know why I put that little comma there. And so what is the total work done on the lift? The total work done on the lift, actually, the total work is the net force times the distance. Okay. The net force though is 0, right? Because we found the net force was 0. So it's 0 times distance times 40 meters, and that's 0 joules. So no net work is done. Now you might ask, well, this is positive work, this is negative work, but they don't cancel out to 0, and that's because we didn't actually calculate the work done by friction. Work done by friction is also negative, and it would be the difference between these two. Okay. Calculate the work done by an 85 kilogram man who pushes a crate 4 meters up along a ramp, makes an angle 20 degrees with the horizontal. He exerts a force of 500 newtons in this direction. call this F, on the crate parallel to the ramp moves at a constant speed. Be certain to include the work he does on the crate and on his body to get up the ramp. Okay. So we got to do free body diagrams. Basically, the work done by the crate that he does is his force times distance. Okay, so that one is pretty straightforward. Let's see. Yeah. So we know the force that he exerts, and we know the distance that he travels. So the work done by the crate is 500 times 4 meters. And that's 2,000 joules. But there's also work that he does to lift himself up, to go up these 4 meters like that. And so I got to do a free body diagram. Well, he has gravity acting on him. He has... The box is pushing back on him. So one of the things we say is that for every action, there's an equal and opposite reaction. That means the box is pushing back on him with a force of 500 newtons. And that must mean he's exerting a force against the ground here. Or the ground is pushing back on. Because how is he lifting it? Is he's pushing, putting his feet on the ground and pushing up with the force here. And so we'll call this, we'll call this normal force, for lack of a better word. Okay, and so how are we going to reconcile? So the work he's going to do is the work of this normal force. It's the work that he's exerting on the ground, which is pushing back on him, and the distance that he has to lift himself. Okay, so we have to calculate what the work he does here on himself is the normal force times times the distance. Okay. Now, to find this normal force, I have to sum up all the forces that are happening on this sort of picture. Actually, this is not really like a good diagram. I'm trying to like sort out what's missing in it, because really he ought to be on the ramp. If he were on the ramp like this, okay, what are all the forces that would be acting? Is we do have a force this way. That's from the box pushing on him. We have gravity. We have a normal force this way. And then we have friction. What's preventing him from sliding down is friction. His legs are providing a force, and he's having a frictional force. The frictional force must be acting in this direction to oppose his motion, right? So that's a better free body diagram of what's happening. Okay. So now, what is the work he does on himself? So this is an interesting question, because it's sort of like, well, what force is he doing on himself? Be certain to include the work he does on the crate and on his body. So, when you're doing, the problem when you're doing with work is you have to identify who's doing what work. The normal force is done by the ground. This is done by the box. This is done by gravity. Friction's kind of the only force we could say like he does, but it's really the work done by friction, so I don't like the wording of this too much. But let's attribute the work that he does to be the work done by friction. Okay. Now, in order to calculate this, I need to establish my orientation. So I'm going to say this is positive x direction. This is the positive y direction. Okay. And I have to assign all of these into each of the corresponding vectors, or I have to break. So the friction's already in the x direction. F is in the x direction. F ends in the y direction. Gravity has two components. It has a component in the x direction and a component in the y direction. And this is 20 degrees. Now, what I really care about is the force in the x direction, because I'm trying to solve for force of friction. So this force here is Fg sine 20 degrees. So if I look at the net force in the x direction, the net force of friction is positive, then F is negative, then Fg sine 20 is negative. And just this is F force of friction minus F minus mg sine 20 degrees. Now this is equal mass times acceleration, but again we move at a constant speed. Moves at a constant speed right here. So thus his acceleration must be 0. And so that is what his total, so this is the equation. So again, remember what I'm trying to find. I'm trying to find the force of friction here. It's equal to F plus mg sine 20 degrees. F is 500 newtons, right? 500 plus his mass is 85 kilograms times 9.8 meters per second squared times sine of 20 degrees. And so this force is 500 plus 85 times 9.8 times sine of 20. And I get the force of friction is 785 newtons. So the work he does here is 785 times the distance, which is 4 meters. And that's 3140 joules. And so the total work he does is the sum of these two, which is 5,140 joules. Add these two together. Okay. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.